Alright, so we're going to be doing probably the hardest video I've done so far. We're going to be doing a little bit of Fourier series in order to prove um, Zeta of 4, which is essentially a related problem to the Basel problem, or the Basel problem. This is not for the introductory calculus student, although you might be able to follow along. It's going to be quite intensive. I'm sure I'm probably going to make some mistakes, but I'll try and do my best in order to, give this topic the sort of the attention it deserves. We're going to consider this fact here, this this general Fourier series for f of x, as long as x is between negative pi and pi. This is true for, I think, any function or any sort of nicely behaving function. Certainly any function that you can integrate. Let's get right into it. We're essentially going to start by finding these constants here, and we're only going to find an and bn, not a0, because we can find a0 by plugging n is 0 into an. But let's start with an. In fact, no, let's start with bn, because there's a nice trick to evaluate bn. Bn is equal to 1 over pi times the integral from negative pi to pi of, and I should mention when we're considering the function f of x is equal to x to the fourth, and I'll make clear in a while why we're considering this function, but just take it for granted this is the function we're studying so far. X to the fourth sine of nx dx. And the trick to evaluating this function is to notice that we have an odd function. Actually, my bad, this is an even function. Even function times an odd function. If you don't know what an even function and an odd function are, I strongly recommend you search them up. But essentially they're functions that behave like even and odd numbers. If you times an even and an odd function, you get just another odd function. Odd. Even times odd is odd. And essentially these bounds are just negatives of each other. So you have a times the integral of negative b to b of an odd function dx. And there's a formula for evaluating this. This is actually just 0. So bn is equal to 0 for all n. Okay, so that one's quite easy to evaluate. Next we're doing an. This is just 1 over pi times the integral negative pi to pi of x to the fourth cosine of nx dx. And we can use similar logic for this. We have even times even is going to give us an even function. And integrating an even function, you just multiply by 2 and change the bottom down to 0. And it's very obvious why this is true if you look at the graph of any even function. But essentially what we're going to get is 2 over pi times the integral from 0 to pi of x to the fourth cosine of nx dx. There's no real easy way to do this from here, but just stick with us on this one. We're going to use DI method to evaluate this, and we're going to ignore the constant for now. Let's just purely evaluate this. Plus, minus, plus, minus, plus, minus. That should be enough. And we're going to differentiate x to the fourth and integrate cos of nx. This is just essentially integration by parts tabular method. I'm sure you've come across this before. And we're just going to do repeated differentiation on these terms until we get to 0. Not much to this, it's quite easy. Boom. And then we integrate, and this is a bit harder. Integration of cosine is just sine of nx, oops, and 1 over, and this is just negative 1 over n squared cos nx. This is just negative 1 over n cubed cosine of nx. Actually, my bad. You don't write that there. Hang on. My bad. I started integrating without actually writing the original function. Please excuse me. Right. Negative. Whoops. We don't need a negative yet. I'm so sloppy today. Alright. Bear with me. You could probably just do this at home. It's not hard, it's just tedious. Okay, finally. And then you just match diagonals, pair them up, then plug in bounds. So we're going to get this, remember the constant is just 2 over pi square brackets x to the 4th, then sine nx over n minus minus, that's just positive, plus 4x cubed cosine of nx over n squared. And then we get 12 with that's minus. I think I'm going to run out of space. 12x squared sine nx over n cubed, and I'll write the rest at the bottom. Then we get minus 24x cos nx over n to the 4th, and then finally we get plus 24 sine nx over n to the 5th power, evaluated at 0 to pi. Now, the cool thing about this is, as soon as you have a sine term and you plug in pi or 0, you're just going to get 0 because these are integer multiples of those, but plug in pi, you get sine of pi n, which is 0 and 0. So, in fact, what we can do is just cancel out everything with the sine automatically and rewrite this in a simpler form. 2 over pi. And what is it? 4x cubed cosine of nx over n squared minus 24. Is it 24x cosine of nx over n to the fourth, evaluated from 0 to pi. Now if we plug in pi, we just get 2 over pi times 4 pi cubed cosine of n times pi over n squared minus 24 pi cosine of n pi over n to the fourth. And obviously if you plug in 0, you got the x here and the x here. That's just 0. And distribute the 2, we finally get 8 pi squared cosine. Actually, we'll factor out the cosine at the end. Over n squared minus 2 times 4 is 48. And obviously the pi's cancel. Over n to the fourth cosine of n pi. And I've just noticed we've got n's on the bottom, so we probably do actually need to work out this a0 here. Oh well. That's fine. This is quite easy actually. A0 is 1 over pi times the integral negative pi to pi of x to the fourth dx, which is just x to the fifth over 5 from negative pi to pi, which you can clearly see is just 2 pi to the fifth over 5. Right, we have our an right here. We have our bn right here. We can finally plug this into this formula right here, because we have our a0 too. So, f of x in this case is just x to the fourth, so we simply get that x to the fourth is 2 pi to the fifth over 5 all over 2 because of the formula up there, plus the sum n equals 1 to infinity. The sine term here just goes to 0 because bn is 0, and we just write the an times cos of nx. This is just 8 pi squared minus, over n to the second power minus 48 over n to the fourth power, n to the second power, n to the fourth power, times cos of, well, we have the cos of n pi, but we also have the cos of n pi here, so actually it's cos squared n pi. And we can notice that when n is equal to a multiple of pi, when n is an integer, cos of an integer multiple of pi is either negative 1 or 1, and it alternates. But when we square that, we just get 1. So in fact, in this series, this just goes to 0, which is quite interesting. Is there another way to show that? I don't think there is. No, there probably is. Still, actually, sorry, did I say that goes to 0? It doesn't go to 0, it goes to 1. And we can show that too by looking at 1 minus sine squared, because sine squared always goes to 1 as well. Well, sine squared goes to 0, but 1 minus 0 is just 1. Anyway, this goes to 1 because negative 1 to 2n is just 1. Believe me. And then we split this into 2, so x to the 4th. I should say this isn't n pi, this is nx. But we're working out, should I say, instead of x squared, we're working out pi squared. My bad. Pi squared. And then we'll do some clever rearrangements and then you'll see. I'm sorry if my video seems a bit unorganized. It's because it is. I don't tend to plan these videos because I like. I've made a mistake here too. I forgot to divide by the pi. This is 1 over pi times that. So this should be 2 pi to the 4th over 5. See, this proves my point exactly. I'm doing this on the fly, which is, I think, I like it because if I make a mistake, you can see that I make a mistake. You know, I'm making mistakes with you, in a way. Anyway, split this into 2 infinite sums. Bring the constant term out of that one. I hope you can see that. I hope that hasn't cut off. I'll rewrite that better anyway. Move this across, we get 4 pi to the 4th over 5 is equal to... You should be aware that this is pi squared over 6 if you take its constant term here. The sum from n equals 1 to infinity of 1 over n squared is pi squared over 6. That's called the Basel problem. It's been solved. I will solve it in a future video actually, but for now take my word for it. This is actually just going to be 8 pi to the 4th over 6 minus 48 times the sum from n equals 1 to infinity of 1 over n to the 4th, which is actually, this part here is what we're trying to work out. Do some simplifications and some rearrangements. Move this to the other side, we get 24 minus 40 pi to the 4th over 30, right, 30, I hope this is right, equals negative 48 sum n equals 1 to infinity of 1 over n to the 4th. This is going to be negative 16 over 30 pi to the 4th, which is negative 8 over 15. And it's looking good. So we get negative, cancel the negatives, we just get 8 over 15 pi to the 4th is just 48 times the sum from n equals 1 to infinity of 1 over n to the 4th. Therefore, this sum is just equal to I ran out of space on my thing. That'd be fine. Let's just how are we gonna do this? I've run out of space, guys. If I can squeeze it in somewhere. This means that if I decrease that to the sum from n equals 1 to infinity of 1 over n squared, oh sorry, n to the fourth, is just simply 8 pi to the fourth over 15 times 48, which is just pi to the fourth over 90, and this is the result. So zeta of 4 is 90. Oh sorry, pi squared over 90, my bad. Pi to the fourth over 90. And there's our result, and I hope that this made sense to you. It certainly doesn't to me. Just kidding. And I want to apologise for the sort of improvised nature of this video. I hope you still found use out of it, and I hope you could see everything, but hopefully my narration made up for any bits that go off the screen, and I hope this was useful. Bye.